Hello everyone, welcome to our today's podcast of transport phenomena. I Himanshu.
And Ayush. Our today's topic is concentration distribution in diffusion with a heterogeneous chemical reaction.
Before diving into the topic, let us first get into one of the most foundational concepts in chemical engineering, that is transport phenomena. Whether you are new to the field or just looking to refresh your understanding, this overview will give you a solid grasp of what transport phenomena, why they matter, and how they shape everything from large scale industrial processes to microscopic chemical reactions. Now let's talk about transport phenomena. So what exactly is transport phenomena? In the most general sense, transport phenomena is the study of how momentum, energy, and mass move through physical systems. You can think of it as physics behind chemical engineering. It's where thermodynamics, fluid mechanics, and heat and mass transfer all come together. These three processes often happen simultaneously and are interconnected. For example, when you are boiling water in a kettle, you have got heat transferred from the burner, mass transfer in the form of vaporization, and momentum transfer as the water circulates. Now let's see the three pillars of transport phenomena. First one is momentum transport, also called fluid mechanics. Momentum transport refers to the transfer of momentum within fluids due to molecular motion and bulk fluid motion. It forms the basis of fluid mechanics and is governed by Newton's law and the Navier-Stokes equation. Key concepts in momentum transport we can say as shear stress, which is caused by velocity gradients in a fluid, represented as tau. Viscosity. Viscosity, a measure of fluid's resistance to deformation. Newtonian fluids have constant viscosity, while non-Newtonian fluids do not. Also, types of flows: laminar versus turbulent. Laminar flow is smooth and orderly, which is low Reynolds number, where otherwise turbulent, which is chaotic and mixed, which says high Reynolds number. Later we can say that Navier-Stokes equation, which gives us fundamental partial differential equations describing how momentum is transferred in a fluid. So applications of momentum transport we can say as designing pipelines, pumps and compressors, also modeling airflow over wings, blood flow in arteries, also reactor and heat exchanger flow analysis.
Next, we will see energy transport, which is also known as heat transfer. By definition, energy transport is movement of thermal energy within a system due to temperature gradients. It occurs mainly through three ways, which are conduction, convection, and radiation. Conduction: transfer of energy via molecular collision in solid and stationary fluids. To solve conduction, we use Fourier's law, which is defined as Q is equal to minus K dt by dx, where K is the thermal conductivity. Convection is defined as transfer due to fluid motion, often coupled with conduction. It is solved using Newton's law of cooling, which is defined as Q is equal to H into A multiplied by T surface minus T fluid, where H is the convective heat transfer coefficient, A is the area, and T surface is surface of temperature, and T fluid is fluid's temperature. And the third type is radiation, which is mainly in the form of emission of electromagnetic waves, which don't require any medium. And it is governed by Stephen-Boltzmann law, which is Q is equal to epsilon T to the power 4. The key concepts involved are thermal conductivity, which is material's ability to conduct heat, heat capacity, the amount of heat needed to raise the temperature, and some dimensionless numbers are also used, which are Biot and Nusselt number. Applications of this is similar to momentum transfer, which is in heat exchanger, furnaces, and insulation. It is also used in cooling of electronic devices or engines, and it is also used to make process equipments more energy efficient.
Now let's see mass transfer, which is molecular and convective diffusion. Mass transfer involves the movement of chemical species within a medium due to concentration gradients, that is diffusion, and fluid motion, convection. Mechanisms of mass transfers are two: diffusion and convection. First, diffusion. Movement of molecules from high to low concentration is the driving force, governed by Fick's first law, which is diffusion flux equals to minus of diffusion coefficient into dc by dx. Also, convection, mass transfer due to bulk movement of fluid, which is combined convection diffusion equations are used in many systems. Key concepts of mass transfer are diffusivity, that is DAB, which is a measure of how easily a substance diffuses into other. Mass transfer coefficient used in convective mass transfer, dimensionless numbers such as Sherwood, Schmidt, Peclet, which characterize mass transfer behavior. Applications of mass transfer are gas absorption and stripping processes, also drug delivery in biological systems, and membrane separation, distillation, and chromatography. Now let us see why transport phenomena is crucial in chemical engineering. Transport phenomena is not just theoretical, it's the backbone of every real-world chemical process. Whether you are in lab designing an experiment or in industry running a chemical plant, you are constantly working with the transfer of momentum, energy and mass. These processes doesn't happen in isolation. They interact and often compete in complex ways. Key reasons transport phenomena is responsible are predicting system behavior. Chemical engineers must be able to quantitatively predict how system will behave under various conditions. Transport models allow you to answer questions like how fast will heat spread through a reactor wall? How long does it take for a reactant to diffuse to a catalyst surface? What is the velocity profile of a fluid in a packed bed reactor? These predictions help avoid trial and error in system design, saving time, money, and materials for the industry owners. Second is design efficient and safe equipment. Proper understanding of transport mechanisms enables the design of optimized high performance equipment such as heat exchangers. You need to calculate heat transfer coefficients to ensure efficient energy exchange without hotspots. In distillation columns, mass transfer efficiency between vapor and liquid phases must be maximized. Also, in reactors, knowledge of how reactants mix and move and how heat is generated or removed is critical to avoid runaway reactions. Moreover, improper design without transport analysis can lead to equipment failure or safety hazards due to thermal stress, pressure buildups, incomplete reactions, or poor product purity.
Next, scaling up from lab to the plant. Lab scale experiments often occur in well controlled conditions, but scaling up a process to industrial scale introduces challenges like non uniform mixing, limited heat dissipation, longer diffusion paths, and also turbulent versus laminar flow transitions. Transport phenomena provides the scaling law in dimensionless numbers such as Reynolds, Prandtl, Nusselt, Sherwood, etc., that guide how to extrapolate the lab data to full scale processes without losing performance or safety. Next, process optimization and energy efficiency. Today's industry increasingly focus on sustainability and energy efficiency. Transport analysis helps in the following ways: minimizes energy losses in heat exchanger and furnaces, reduces pressure drop in piping system, improve catalyst utilization in reactors, enhance separation efficiency in absorption, stripping, or extraction units. With accurate transport modeling, you can simulate different processes, configuration, and choose one with minimal operational cost and maximum yield.
Without understanding transport phenomena, you are essentially operating blind. Decisions would rely on empirical guesswork rather than predictive modeling. These risks include over-design, leading to unnecessary cost, under-designing, leading to unsafe or inefficient systems, undersizing, leading to unsafe or inefficient systems, failed scale-up, product quality issues, and increased energy consumption.
Now that we have discussed an overview of a subject, let's dive deep into the topic that we are going to use in the topic that we have chosen, which is one of the pillars in transport phenomena. In our case, that's mass transfer. Let's begin with the idea of mass transfer. At its core, it's about how material, which is usually a chemical species, moves from one place to another. It might move from a region of high concentration to a region of low concentration. That movement happens in gases, liquids, and even in solids. And it's essential in everything from separation process to reaction inside a catalyst. Specifically, in mass transfer, we'll dive deep into diffusion, Fick's law, and how diffusion couples with chemical reaction. Mass transfer is basically movement of species which include atoms, ions, molecules in a mixture. It can occur due to following gradients: concentration gradient, which is called diffusion, bulk motion of fluid, which is known as convection, and sometimes it is a combination of both. In most chemical processes, diffusion plays a key role, whether it's in separation units like absorbers or reactions inside catalyst pellets. Now, diffusion, the molecular mechanism. Diffusion is driven by random molecular motion of particles. Even in a perfectly still fluid, molecules are constantly jiggling around due to their thermal energy. When there is a concentration gradient, more molecules move from a region of high concentration to a low concentration, causing a net transport. This movement is governed by mathematically using Fick's law.
Now we will see about Fick's first law of diffusion. Fick's first law is analogous to Fourier's law of heat conduction or Newton's law of viscosity. It relates the molecular flux to the concentration gradient. Now we will see the mathematical form of Fick's law. J, which is molar flux, is equals to diffusivity into concentration gradient. Here the negative sign indicates that diffusion occurs from the concentration gradient. Now we will see Fick's first law of diffusion. Fick's first law is analogous to Fourier's law of heat conduction or Newton's law of viscosity. It relates the molecular flux to the concentration gradient. Its mathematical form is molar flux J is equals to minus of diffusivity of A into B into concentration gradient of A. Also, here the negative sign indicates that the diffusion occurs from the concentration gradient from high concentration to low concentration. Now we will see an example on one-dimensional diffusion through a film. Consider a stagnant gas film of thickness L with species A diffusing from left to right. The concentration at the left face is Ca1 and at the right face is Ca2. Now assuming steady state, that is Fick's first law, constant diffusion coefficient and no generation or consumption inside the film. Now on integrating we get Ja equals to minus of dAb Ca2 minus Ca1 upon L, which is the length. This is the final required molar flux through the film. On moving to Fick's second law, which is unsteady or transient diffusion. Fick's second law applies when the concentration changes with time, like when you suddenly introduce a species into a medium. That is unsteady or transient diffusion. General form of Fick's second law is concentration with respect to time is equals to dAb into d square concentration upon dx square. This is partial differential equation that describes how concentrations evolve over time with space.
Next, we will see diffusion with chemical reaction. In many practical systems, diffusion and chemical reaction occur simultaneously. A classic case is a porous catalyst pellet, where a species diffuses and reacts inside. Let's consider the steady state diffusion of species A into a slab with first order reaction with the following kinetics. The governing equation. If we assume 1D diffusion, no convection, and constant properties, we can write dAb d square Ca upon dx square equals to kCa, which on rewriting can be converted into a second order linear differential equation. Another important topic is effectiveness factor and Thiele modulus. In catalyst design, we often use these two dimensionless numbers, Thiele modulus, which is defined as L into under root K upon dAb. It compares the rate of reaction to the rate of diffusion. If it is very less than 1, the reaction is slow, diffusion is fast, which is considered as reaction limited. If it is very greater than 1, reaction is fast, diffusion is slow, which is diffusion limited. After that, effectiveness factor is defined as actual rate of reaction upon rate if entire volume were at surface concentration. This accounts for how much of catalyst volume is actually utilized. If diffusion is limiting, only the surface is active.
Now we will see diffusion in homogeneous reactions. A homogeneous reaction occurs when all reactants are in same phase, for example, gas in gas and liquid in liquid. Because the medium is uniform, diffusion is typically fast and efficient compared to other. For example, the reaction between nitrogen dioxide and carbon monoxide giving nitrogen oxide plus carbon dioxide is an example of homogeneous system. In homogeneous system, diffusion occurs very fast. Because of no phase boundaries, molecules move freely and collide frequently. Uniform mixing, stirring or thermal motion ensures even distribution in the system. Also, high collision frequency results in faster reaction rates. An example, let's see a real world example of homogeneous systems. A classic example is the ozone decomposition reaction in the atmosphere, where ozone disintegrates into oxygen. Here, ozone molecules diffuse and collide in the gas phase, leading to the rapid reaction kinetics. The reaction is 2O3 gives 3O2. Now, diffusion in heterogeneous reactions. A heterogeneous reaction involves reactants in different phases, that is solid and liquid, solid into liquid or gas into solid. Here diffusion is more complex because molecules must cross phase boundaries. An example of this is rusting of iron, a solid metal reacting with oxygen gas and vapor, where iron reacts with oxygen and also with water to give iron hydroxide. Why diffusion is slower in heterogeneous reactions? Because of interfacial barriers. Reactants must adsorb onto surface before reacting. Also, because of limited contact area in case of heterogeneous reactions, only surface or atoms of molecules participate, for example of catalyst. Diffusion control kinetics. Reaction rate depends on how fast reactants reach the interface. Now, role of surface area and catalyst. To speed up heterogeneous reactions, we can either increase surface area or use catalyst. For example, on increasing surface area, powder reactants instead of bulk solids, or in case of using catalyst, using platinum in catalytic converters helps gas solid reactions. Industrial example of heterogeneous system is Haber process. In ammonia synthesis, nitrogen and hydrogen gas diffuse onto a solid iron catalyst. Reaction occurring is N2 plus 3H2 gives 2NH3. The reaction is limited by how fast gas molecules reach the catalyst surface, which is iron surface. Now let's compare homogeneous and heterogeneous reactions. First we will see phase. Homogeneous occurs in same phase. For example, gas in gas or liquid in liquid. In case of heterogeneous, different phases are there, like solid in gas. Now on moving on to another aspect, diffusion speed. In case of homogeneous, diffusion speed is fast, and in heterogeneous it is slower. Also, in case of homogeneous, uniform mixing is there, and in case of heterogeneous, interfacial resistance is present. Now, reaction rate of homogeneous is usually faster, while it is slow in case of heterogeneous. An example of homogeneous reaction would be acid base neutralization, and for heterogeneous it would be combustion of coal. Now let's summarize between homogeneous reaction and heterogeneous reaction. In homogeneous reaction, benefit is there from rapid diffusion leading to faster kinetics, and in case of heterogeneous reaction it is limited by diffusion, so it requires strategies like increasing surface area or using catalysts to increase surface area. Now, understanding diffusion is crucial in many fields. For example, in pharmaceuticals, drug dissolution depends on diffusion in liquids. And environmental science, air pollution dispersion is a diffusion process. In material engineering, coating and corrosion processes rely on diffusion.